All right, so I'm now going to talk about the complex function method of approximating the derivative. So this works particularly well in MATLAB because, as I said before, MATLAB oftentimes overloads functions. It's like the functions can actually be evaluated on complex numbers instead of just real numbers. Okay, so let me sort of briefly recall what the issue is. So recall that you can have f prime of x, and it is approximated by f of x plus h minus f of x over h plus an error, which is big O of h. Okay, so the basic problem, if you will, with these finite difference type methods is that these differences involve taking the difference of two numbers which are very close to each other, which results in round-off error, and you lose significant digits of accuracy when h is very small and when those two function values as a consequence are very close to each other. On the other hand, if your h is moderate, then there is the truncation error term. So you have to balance. It's like it's like the trade-offs between h being too small, it's like and you suffering from significant round-off error, and h being too large and you suffering from significant truncation error. Okay. So, and again, the real problem is that you have this difference of the function values which are close to each other. So if you remember, the way one does this, right, is or the way one gets a formula like this, it involves looking at the Taylor expansion. Okay, so this sort of formula, right, is derived from the Taylor expansion of f of x plus h, right? Okay, so we're going to do something similar now, but in a sneaky way. Okay, so let's consider the following. So let's consider f at x plus h, but not just hi times h, right? So x plus I times h. So now we're evaluating f, it's like on a complex number, okay? And then we can again do the Taylor expansion of this, right? So this then becomes f of x plus I h f prime of x plus I h squared over 2 f double prime of x, right? Plus I h cubed over 6 f triple prime at some unknown value. Let's just say c. Okay. So what should we do now? Okay, so we want to have an approximation of f prime. Okay, so the f prime is here, but you have a complex number now. Okay, and the nice thing, of course, is that these are all the derivatives of f, right? All these real valued things. Okay, and then the complex part just comes from, it's like these coefficients here. So I can take the imaginary part of this equation. So I take the imaginary part of f of x plus I h. Okay, and then that drops off the first term. This is equal to h times f prime of x. And then the next term is this term, right? So you have an I cubed, right? So that's a minus I. So you have a minus h cubed over 6 f triple prime at c. So this is an equality, okay, where again c is some indeterminate value. It's like in yeah. Anyhow, all right. So let's not worry too much about that. Okay, so I can divide throughout by h now. I get 1 over h, the imaginary part of f of x plus I h, right, is equal now to f prime of x minus h squared over 6 f triple prime at c. Okay, and that way, and then reordering, I get f prime of x is equal to 1 over h, imaginary part of f x plus I h plus h squared over 6 f triple prime at c. right? So this is a big O of h squared term. All right, so that's the truncation error, which we have before. But now it's like we have something quite magical, if you will, right? So this is my computable approximation. But you'll see that this doesn't suffer from the issue which plagues this particular finite difference approximation, right? The reason why this finite difference approximation is problematic is because it involves the difference of two function values which are very close to each other. So now we don't have a difference. I'm just looking at the imaginary part of f evaluated x plus ih and dividing it by 1 over h. So now I'm not subject to round off here, okay? And so I can take h to be small and not suffer from round-off error, and that's sort of consistent with wanting h to be small in order to make the truncation error small. Okay, so actually, in addition to that, because the error is big O of h squared, you only really need h to be of the order square root of machine precision in order for this term to be extremely small, right, of the order of machine precision. And then this term is, again, not subject to round-off, so you don't have a problem coming from this as well. So it turns out that if you take h of the order of anything between square root of machine precision to machine precision and you evaluate this term, then you get a approximation of the actual analytical derivative, which is up to machine precision in accuracy. Okay, so this is a very nice way of computing derivatives. It's like functions if they happen to be real analytic. So it's important, of course, to realize that at the heart of all of this, right, is your ability to write down a Taylor expansion, and this requires that the function is real analytic. But many of the functions it's like which we work with in practice are real analytic, and MATLAB's ability to function overload then allows you to evaluate those functions on the complex plane instead of just in reals. Okay. So this is particularly nice. And in addition to that, it's like you can sort of extend this to sort of vector valued functions where instead of taking x plus ih, you have to take x plus I sort of e sub j, where e sub j is the vector, right, which has 1 at the j component and 0 elsewhere. And then that gives you the derivative of the vector valued function f. It's like respect to the xjth component, right? And then so you have to do these. So in order to compute something like the Jacobian of a sort of vector valued function, you have to evaluate these sort of complex evaluations of the vector valued function at a bunch of points, but that's not so hard to do in order to assemble it's like this this Jacobian. Okay, but nevertheless you can use this it's like quite nicely if you're ever tasked with implementing, say, a Newton solve, and you have to assemble, it's like a Jacobian matrix. It's like you can use the complex derivative formula if you happen to be working in MATLAB and working with functions which are real analytic. So anyway, so that's kind of a nice trick. It's like to be aware of. It's a useful thing to keep at the back of your mind. So let me just stop here for now.